Hello, my name is Dr. Nicholas Larrosa. I'm a lecturer in structural integrity at the University of Bristol, and the title of my talk is Application of the Theory of Critical Distances within a Defect Screening Approach for Inline Inspection Datasets. So this, to provide a little bit of background, this project was funded by BP and was in collaboration with the University of Manchester and University of Malaga in Spain, and it was mainly targeted to try to develop an approach in which the pipeline operator could easily locate, identify, and rank defects based on severity. So that then would allow them to perform informed decisions and go into more detailed analysis in those defects that were considered to be more critical. That was the main project, or that's the main part of this talk. And there was a side project that was mainly targeted to try to understand how non-sharp defects can be assessed from an integrity viewpoint, so as to avoid the recharacterization of defects failing the local thinning area geometry check to be characterized as cracks. In this approach, we are just assuming fixed values of defects size and dimensions. We are not considering in any way the scatter in the error in the measurements. But of course, that's something that needs to be considered in real applications, and it's within and can be easily implemented in the approach that we will be explaining next. So the objectives of the project and what we will be presenting in this next few minutes is to evaluate relative criticality of defects within the structure, reduce the number of defects requiring detailed analysis, and evaluate the severity of defects based on the actual 3D dimensions. We're going to present here a two-step defect screening procedure, which is formed by a geometry-based filter and an elastic stress-based filter. This stress-based filter is based on the theory of critical distances, and that's what we will be discussing today. This part one, and we will not focus on the actual life assessment or strength assessment, remaining strength assessment, which is the part two, and mainly depends on the loading conditions and the environment and the characteristics of the component and environment. Okay, so the geometry-based filter uses two parameters, which is one of these is sphericity. Sphericity gives you an idea of the roundness of a component, and it's basically comparing the surface area of a sphere with the same volume of the defect, and that will give you a metric between 1 and 0. 0 would be a flat 2D defect, and 1 would be a sphere. So basically saying if the surface areas match, that's a sphere, because you're comparing, of course, to a sphere. If they don't match, and because the surface to volume area of the sphere has the greatest value of sphericity, that's the highest value of sphericity you can get, and therefore all values will be within 0 and 1. Of course, we do not consider any sort of microtopography or shape, we will assume the defects are semi-ellipsoidals, and as a result, we will be focusing mainly in this area where we have a metric of roundness or sphericity, but we don't have a metric for regularity. If we could count with a regularity metric, then we will be able to distinguish and span this range of defects with same sphericity but different regularity, which is not the case for this project. So that's probably could be considered as a flaw of the project. Right. So what we do, the main idea is that we defects with low value of sphericity and defects with high value of depth will be the most severe. So then when we plot this line, these defects could be considered those to go and look first in terms of criticality, and we could probably avoid analyzing in very much detail defects in this area, right? So it will depend on the industry or the criterion used or what sorts of levels of conservatism is acceptable. So then you would probably move this line towards this point, and you would probably be more interested in characterizing all these defects. But then you're still reducing the data sets for analysis. Okay. So the next step is to, once you have a reduced set of defects, then you need to be able to make a ranking. And we use a theory of critical distances, in particular the point method, to do that. And as you know, to perform a TCD analysis, you need this parameter L, which for fatigue and fracture has different expressions, but are still related to the material properties. And once you do that, you can perform a stress analysis and elastic stress analysis and calculate the stress field ahead of the defect tip, and then this is the distance ahead of the distance tip, and then you can calculate the stress at a point value of L/2, at a distance of L/2. And then for this case, for this kind of there was not a nice choice for a marker. So defect 1 and defect 2 are the most severe and the least severe defects respectively. Once you do that, so then we can say that we have been able to rank defects based on stress field. Okay, so what we will do next, if we will we will perform a real case study of a 12-inch riser. This data was provided by BP. So the data was for more than 11 kilometers of pipeline, where around 1,800 anomalies were detected, of which 1,750 were pits, and most of them were internal defects. And that's pretty much obvious, because inside of pipeline there's a lot of more nasty things than outside, where the only aggressive environment is seawater. Okay. We also have the maximum allowable operating pressure. So these are design values, and we have the dimensions of the pipeline. So with all of this, we are able to apply our procedure. We develop a rendering tool to allow to have a kind of a clear view of where all defects were deposited, and also if there were specific locations where a higher density of pits were can be distinguished. Right. So from all that data, it was pretty obvious that most pits were located at the bottom of the pipe, the pipeline, and that's also related to condensation. So most of the condensation, so most pits were also, more pits were created due to condensation, and the other typical or important data was that, of course, as I said before, most pits were internal, right, with a very little number of ones were external. Once we calculated sphericity for all those defects, we realized that unfortunately most defects were quite blunt and quite volumetric. So as far as from a sphericity perspectives, there was a little, or the least number of defects were considered to be more severe, but there's also a need to be able to understand how those systems were located in the structure and how long or hard was the size of these defects. So, following the same procedure explained before, we put all defects within a graph of sphericity versus non-dimensional flow depth. T here is the thickness of the pipe, and we see that there's a big range of defects which probably are away from the area of interest, and there are a few defects that could potentially be more severe, and that we should probably focus on them first. Depending on the criteria, as I said before, you could reduce your 1,750 defects or pits to a different number. In this case, I'm showing you through 3 different criteria with different levels of conservatism. And for the case of study here, and for the critical distance method approach, we picked the easiest one, which was the one with the green line, which only focuses on 4, right? Which are these 4. We use the rendering tool to create STL files and to input those files into FEA analysis software, and to create FEA meshes and perform the elastic FEA and obtain the stress fields ahead of the different notch tips. We also needed some material properties that it was taken from the PhD thesis by Dr. Olufatova from the University of Manchester, supervised by Professor Bob Akett. So with these values, we were able to characterize and calculate the L parameter and the critical distance method. Here are some basically these slides is showcasing the FEA analysis for each of the specific 4 pits, and is giving you a collapsed in plane view of location on the cross section of the pipeline of the different pits. As I said, they were all internal, and but of course they were located in different parts in terms of length, position, and the longitudinal position of the pipeline. So here are the different stress fields for the different pits, and we can see that we have stress fields for pits in different locations. We selected the most severe stress field to display in this graph, but we calculate, of course, the stress fields in the different directions to be able to capture the most severe one. So for most defects, the more analyzed in this case, the most severe case was in the radial direction, whereas for pit 1, the most severe case was for the axial direction. Okay, and it was evident that pit 2 and pit 3 were the most severe ones. With using the expression for the unnotched hoop stress in a thick wall pipe, we were able to calculate the stress needed to apply the critical distance method and evaluate the remaining fatigue strength of the structure by only having a specific pit, either pit 1, 2, 3, or 4, and that will give us an idea of how this the severity of each of these pits. So we did that, and we evaluate the fatigue strength of the structure with pit 1, pit 2, pit 3, and pit 4, and we found out that pit 2, of course, and pit 3 were the most critical ones. So you don't need to do this calculation to evaluate that, because that was pretty evident from the stress fields. But in any case, that was it was useful to have it's useful also to have a stress value, a stress range value that you can then link up to the operating conditions. In this case, the value of P used here was the maximum allowable pressure, okay, which was 20 megapascals. Right. So this is just displaying the same results within the graph of sphericity versus non-dimensional flow depth, and basically showing you that intermediate values for sphericity and flow depth gives you the most critical pits, where in this case you have a very deep pit but quite blunt, quite more three-dimensional, and here you have a quite shallow, a quite flat pit, but only represents 10% of the thickness, whereas this one represents 20%. So this was a shallower but more flat pit. So to sum up, we have presented a screening methodology proposed to reduce the amount of data requiring detailed analysis from data obtained during inline inspections. The method uses the defect sphericity and the pit depth to thickness ratio as a first filter, and the critical distance is then applied as a simple and consistent approach to generate a ranking of flaws. The approach shows that the amount of pits requiring detailed analysis can be reduced significantly. Well, that's pretty much it. I'm really glad that I was able to participate in this. Thank you very much for this opportunity, and I will be looking forward to discuss my work with you all. Thank you.